Hi, this is Jim Janossy. I'm here to give you a little bit of a mini lecture on what you see on the screen behind me. Now, I have a bit of a problem because I only have one little tripod and I'm sort of leaning down to get my face into the picture just so that you see who's talking before we start focusing on that slide that you're seeing right over there on that computer screen. That's what I'm going to focus on for the next several minutes. I just want to let you know that that slide that we'll be focusing on, we're going to use that as a table of contents to the material in Unit 2 here in CSC 200. I'm going to give you a broad brush view of the history leading up to the development of the kinds of computers that we have today. So this will be quick, it will cover a long expanse of time, but it's towards the end of this period of time, essentially the last 100 years, that we're going to see some very interesting developments leading up to the kind of computers that we have today. You'll notice there's a purple ball at the upper right corner of this screen. That's going to be the bouncing ball that you follow as I go through and quickly give you a rundown on the different pieces of time and the pieces of history here leading up to the development of the kind of computers we now use. Let's take a look at ancient history. 30,000 years ago, nothing in the way of computers. In the ancient times, nothing then either. Roman Empire. Science was sort of coming together during the Roman Empire and the Greek Empire that preceded it, but here in the Middle Ages, a lot of knowledge was lost, at least in Europe. So we're not really considering much of the development of that period of time, or even here in the Renaissance, although in the Renaissance people started reviving a lot of the ancient knowledge. It's only down here in what I would call the Age of Invention, starting around 1830, that we start seeing some people actually thinking about mechanizing the process of computation. So Charles Babbage came up with a machine that was based on the technology of the day. It was more like a mechanical calculator called the difference engine. One of the videos you're going to see associated with that little red ball that has the number 1 in it is a video in the playlist associated with this that will show you how a reproduction of this giant calculator would have worked with rotating gears and various other sorts of things. Very primitive, but a definite step ahead in thinking about how to mechanize the process of computation. Here we see the electric light, and you'll notice that I've given you in the videos, about 19 seconds of one of these bulbs just starting to glow. We kind of take this for granted. In fact, we're abandoning light bulbs like this because they're rather inefficient. They put out a lot of heat in addition to light, so it's not a very efficient use of electricity. But the electric light bulb was a very big deal when it was invented in the 1870s, because for the first time you could conveniently, without burning something and taking the chance of burning the house down, you could actually light the place up. Electricity was being harnessed and commercialized at this time, and this was one of a number of inventions that Edison made that of course put his name on the roadmap of technology. But here we have something that was built upon the light bulb called a vacuum tube. It came about because people noticed that the inside globe, which had a vacuum, accumulated a kind of a coating, and they wondered where that came from as the light bulb operated. Edison looked at it as kind of a detriment because it reduced the amount of light that the bulb would produce. But others discovered that it was a flow of electrons that was emanating from the heated filament, and they put that to use in the vacuum tube by putting a positively charged metal plate in there. The electrons would flow only from the heated filament to the positively charged plate. Electrons are negative, they would flow in that direction. So this vacuum tube of that form would at least change alternating current into direct current. And there are different uses for those different types of electric current. Also, it was discovered that by putting a metal grid in between that filament and the plate that was collecting the electrons, a small signal on the grid could cause a great change in the signal flow from the heated filament to the plate. So an amplifier could be built, and soon thereafter it was figured out how to make that into an oscillator. That is something that would produce radio frequency waves and generate waves that could then be transmitted. Prior to that time, mechanical devices were used to create the kinds of signals that ships would use to communicate in Morse code between themselves on the shore. Didn't take very long for radio to be commercialized. It was a big leap of thinking on the part of a fellow named Sarnoff, who later ran RCA, the Radio Corporation of America, a huge corporation at the time. Sarnoff figured out that radio would be better than just for point-to-point communication, that you could set up a transmitter and many people could listen to that broadcast. In 1920, the first of the radio stations came on the air. About that same time, not very long after, in the 1920s, Philo Farnsworth was experimenting with how to transmit images, in other words, black and white television, electronically, by scanning an image, breaking it up into signals that indicated the intensity of the light at different points, and then painting that image on a screen. Now, that painting the image on a screen is pretty important for us because that's, of course, where computer screens came from at a later date. A little bit of a cul-de-sac here. There was a fellow named Bayard in England who continued to carry the torch for mechanical television, rotating discs and various other things that would break the image up, transmit it, and then reassemble it. By about 1930, this was given up as any kind of a practical mechanism. It was realized that electronics with no moving parts was the way to handle this kind of communication. Unrelated development in the 1930s, Alan Turing, among other academics, laid the theory for how you could use a machine that could store bits, manipulate them according to what we would now call a program, a series of repetitive steps based on the fact that an algorithm, that is a recipe really for how you will carry out this computation. Turing actually demonstrated this with something called the Turing machine, and there's a video or two in the playlist for you about this. It's not essential that you understand how the Turing machine works. The important thing is to understand that a stored bunch of instructions on how to process data repetitively could be used to implement a calculation. And it's based on that definition of an algorithm, which you'll find in the workbook as part of the material that I've prepared for you on Alan Turing and the Turing machine. It wasn't very long before various people in academia tried to implement a machine that actually would do what Turing's theory laid out. A number of people were somewhat successful in doing that. There's a fellow who taught in Iowa and his assistant at Nassau, and a fellow named Barry, who actually did this. They built a computer in the late 1930s, and it actually didn't go anywhere except in their own lab to demonstrate some concepts. Another fellow named Zusa actually took computers farther in Germany, but we never heard much about that because that was Nazi Germany and they weren't letting out very much in the way of information. During the Second World War, a machine was constructed in England called Colossus, which used a combination of technologies, including electronics, to help decipher the codes that the Germans were using so that communications could be intercepted. But it wasn't until after the war that a machine developed in the academic world called ENIAC, Electronic Numerical Integrator, or something or other. Well, the letters ENIAC stand for something, and it escapes me right now what it is, but it was a big machine with 18,000 vacuum tubes in it. And those vacuum tubes, some of them would be dedicated to storing information as bits. Others would be dedicated to interpreting various bits as instructions, just like a Turing machine. So the program was stored there, and a series of repetitive actions could be used to perform computations. This was a very big deal. This meant that the computer was practical, although at that time the technology to implement it was so large that the computer actually filled up a 3,000 square foot room and people could walk into the computer. It was also programmed in an awkward way with a bunch of cables. They hadn't really come to the point of storing the program inside the machine as well as the data. Another development that came along in the late 40s, the transistor. The vacuum tube was a successful electronic valve. It could control the flow of electrons, but it generated a lot of heat. It was expensive to manufacture, and eventually, like a light bulb, the filament would wear out. A transistor overcame all of that and did the same thing. It allowed a small signal to control a larger flow of electrons. It was a piece of semiconductor material with 3 wires attached to it in a special way. Material science had advanced quite a bit at that point to understand how, at the molecular level, things could be done to encourage these materials to mimic what a vacuum tube did, that is, to control the flow of electrons or to act as a switch to store a bit either with the current flowing or with the current not flowing, 2 different conditions that could, of course, represent digital memory. It wasn't very long before the theory that was developed in the 30s and the practical implementations that were tried out in the 40s resulted after the Second World War in the commercialization of computing. It wasn't IBM that did this. It was a company named UNIVAC, that sold the first computer to the U.S. government to do the census in 1950 to help process that data, which was ironic because back in the 1890s, when a fellow named Hollerith invented punch cards, the Census Bureau was the first buyer of that device to automate the 1890 census. So they had a history of trying to automate these massive computations that are done all in a crunch period of every 10 years. The computers built at that time, by modern standards, were very slow and very expensive and very limited capacity, but they actually did work, and businesses would buy them. It really was kind of interesting that IBM in the 1940s, they were doing a very large business with mechanical tabulators using punch cards, and the fellow who ran IBM, a fellow named Watson, really thought that in the 1950s there would probably be about 5 computers sold in the world because they were so expensive and took so much time to set up and keeping them up that only governments, he felt, would be rich enough, wealthy enough to afford these machines. Well, of course, his prediction was way off because of what we'll see that happened in the next several years. The IBM 650 was a successful machine in the 50s, the 1950s, and IBM, that's where it stuck its foot into the water of computing and really got big. It was a very large corporation, and it essentially took over the market with the development that happened next, which is standardization. In the 1960s, IBM came up with a model of machine called the IBM 360, and it wasn't one machine, it was a whole series of them. So you could buy a small machine, actually you would lease a small machine. When you outgrew its capacity, IBM could wheel that one out, bring in a bigger one, charge you more money, and you wouldn't have to rewrite your programs. That was a problem with the early machines because they were very unique creations. Every time you bought a different machine, you had to write your programs all over again, which was kind of foolish. And by standardizing on the architecture of a machine, mainframes, IBM really dominated the business. Just as happened in the 40s, where the transistor replaced the vacuum tube, something called the integrated circuit didn't exactly replace the transistor, but it shrunk the size of the transistor down. People realized that instead of manufacturing transistors on slabs of semiconductor material and cutting them up to package each transistor separately, and then wiring them all together, why not build the circuit first and essentially grow the transistors on the semiconductor already wired together? And that's what integrated circuits were. They were developed as part of the research that supported the military at the time and then rapidly commercialized. The fact that the circuits were standardized and were manufactured all put together with thousands of transistors on one circuit component meant that the cost was much lower than the cost of wiring all this up, which meant that smaller computers called mini-computers could be developed and sold at less cost than mainframes, essentially for dedicated purposes, some specialized things that mainframes didn't do well. Computers, when they came into organizations in the 60s, generally wound up in the accounting department because what do computers do? They compute. They crunch numbers. Where are the numbers in the corporation? Well, the accounting department and the financial area. So big computers were used there, but scientists had computational needs that they couldn't necessarily do very well on the big machine that was running the accounting for the firm. So these little mini computers crept in. Now, they weren't so little. They still cost hundreds of thousands of dollars, but they were built with integrated circuits, which made it possible to sell them at that much lower than the millions of dollars cost that each mainframe might run. Well, the development continued. Mini-computers aced out mainframes. Pretty soon, microcomputers aced out mini-computers because the same shrinkage of the circuitry made it possible to assemble a few components on a circuit board called a motherboard and build and program a much smaller computer. And the first of these, the IBM PC, the Apple II before it, and a few others, well, actually several others that sort of came and went, just like when cars were invented, there might have been 100 different brands, and eventually the market thinned everything out to just a few brands. And now, essentially, we have two architectures of personal computers. Apple, which manufactures all of its own equipment and supplies all the software. Nobody else does that. That's one reason why two factors apply to Apple computers. They're extremely well made. The company has a fantastic engineering and design group, but of course they can charge more for their equipment because it is a monopoly. They're the only ones who make it, and there isn't any competition, not with the quality that Apple puts into its machines. So their machines might cost 3 times as much for a laptop as a PC, The difference at the other end of the spectrum, the PC architecture was widely copied, and we have thousands of manufacturers who make these commodity products. Microsoft supplies the software for it, but doesn't have any control over the manufacture of the machinery. And that means, of course, it's a different type of machine. It's very credible. It costs about a third as much as a laptop of the Apple variety would cost, but you pay your money and you take your choice. They're both very credible families of equipment. When personal computers, microcomputers, were developed, they grew out of the mini-computer environment, which had no heritage in mainframes. They didn't use punch cards on mini-computers. They used a teletype device, and that was replaced eventually by a computer screen, a keyboard with a terminal, a screen that you could type on, and the kinds of applications that were aimed at mini-computers were things that we now recognize as office automation. Things like email, things like word processing. When the PC came along, one of the biggest developments that drove Apple forward with it and sold thousands of machines was a program called VisiCalc, which was a spreadsheet. It was the first time anybody could actually do that type of accounting manipulations rapidly and reliably on a small device that didn't cost very much. That actually built the success of the Apple II computer. Those machines were sold just to run VisiCalc in many cases, and people loved it. It changed the way a lot of business operated, just that one development. Eventually, spreadsheet software became available on IBM PCs as well, and since the 80s, we've had these two families of equipment. But at the time they were invented, you had to be kind of a programmer mentality to use them. What was called the command line interface, that is, you typed commands on a screen that kind of looked like an electronic typewriter. You had to know the commands, and you had to interpret what came out that was rather cryptic in the same way. Here's a development that occurred in the late 1980s and into the 90s and onward. Steve Jobs saw a development at a research center run by Xerox where a graphical interface was being used. A device called a mouse, which we now take for granted, was used to point on the screen at various things, and that's how actions were initiated. That kind of a graphical user interface, a GUI, was revolutionary. And the Macintosh, released in 1984, was the first computer to have it. It was soon copied by the Windows environment. It's from those origins that what we have today in terms of the different versions of Windows and the graphic orientation of Apple computers comes from. So that's a development you should associate with just the late 1980s, about the same time that the web, which had come about actually as an academic and a military invention in the late 1960s, adopted more of a consumer orientation about the same time that a graphical user interface came in. So I would say about 1990, you could think about that as when all of these things came together. Affordable small computers that had a graphic interface so ordinary people could use them, and connections to the web, which would allow machines to share information across great distances very readily. The web tended to minimize any problems with different equipment because the web communication is very standardized. It doesn't matter what kind of machine is serving up the images that you get on the web and what kind of machine is presenting them. Apple's talked to IBM, has talked to many computers running a Unix operating system, and they don't even know who they're talking to because the communication has been standardized. That's one of the big things that the web contributed to the development of the world of automation that we have today. Now, this timeline runs out at about 2000. After this point, of course, a lot of innovation occurred, and what we see is that computers got much smaller. Essentially, telephones became computers. When you talk about a smart telephone, you're really talking about something that's as powerful, well, let's say much more powerful than this original ENIAC computer of the 1940s, and it's in a cell phone. And it can do a lot of computations and a lot of things, and sort of as an incidental thing, it lets you communicate as a telephone. So this device, the smart cell phone, really is revolutionary, taking computational power out of some fixed location, becoming a mobile device. And of course, then the cell phone grows up into tablet computers, popularized only a few years ago by Apple and now copied by just about every vendor under the sun who wants to get some of that business. That's about where the world is right now. Now what you're going to do is learn a little more detail about all of these things that I've touched on only briefly as you start going through the 40 or so pages of Unit 2.